Hello, my name is Anush Murthy, and I'm on the Encoding Technologies team at Netflix. Today, I'm going to give you an overview of Cosmos, the microservices-based media processing platform that the Media Cloud Engineering team has developed in partnership with Encoding Technologies. We'll be using the Video Encoding Service as an example as I go through this talk since I am from the video team. But the concepts discussed here are widely applicable for all other media processing that Netflix undertakes in order to spark member joy. Finally, while I'm the face and voice for today, I only represent both Media Cloud Engineering and Encoding Technologies. For as you shall soon see, Cosmos is truly a monument to collaborative development. Let's get started then. Before we head to Cosmos, a quick overview of the teams is in order. Encoding Technologies, or ET, a name that's a bit reductive but that has stuck, provides not just audio and video encoding expertise, but media processing expertise for all of Netflix. This includes inspection of delivered assets, interpretation of media deliveries, and generation of derivative media such as video, images, audio, and text that enables the Netflix member experience. ET also provides support for production and studio use cases, serving as a one-stop shop for media processing, from creation to delivery. While ET houses media experts, our sister Media Cloud Engineering team consists of giants whose shoulders we stand upon in order to spark member joy. MCE provides ET with the underlying platform and infrastructure that enables media processing at scale. MCE also supports the studio side of the business by building and operating workflow and data infrastructure services, which allows other teams to focus on building business applications instead of on infrastructure. Today, there are two main workflows that support media processing at Netflix. One that is studio focused and relates to content creation, and one that is member focused and relates to content delivery. There are a few use cases outside of these workflows as well, but the two main workflows account for a majority of media processing at Netflix. The two workflows, Sagan and Tapas, have varied requirements. Sagan supports ad hoc media processing, and typically there's a human at the other end waiting for their workflow to finish, and so Sagan is extremely latency sensitive. Projects are also short-lived, and typically there is a single deliverable that comes out of the processing. For example, a watermarked muxed media file that can be used for creating subtitles. Tapas, on the other hand, is our member-facing workflow and is throughput sensitive, since typically there is a window between the ingest and the time the title has to go live on the service. Additionally, since Tapas supports content delivery, each Tapas project generates a bunch of derivative assets, including audio, video, and text, and it also generates a host of media-related metadata that needs to be propagated to downstream tables in order to enable seamless playback. Projects are long-lasting. You wouldn't want the sixth episode of Squid Game, Ganbu, to disappear off the service now, would you? Media processing infrastructure then needs to support both these extreme use cases. We did not get to where we are in one fell swoop, of course, and the media processing needs here have grown over the years to what I described in the previous slide. With growing media processing needs, the media processing platform and infrastructure has grown as well, constantly learning from its predecessors and moving from monolithic script-based workflows that were rigidly developed around the use case to serverless runtimes that allow for greater flexibility by composition of microservices based on application and business need. With that quick history lesson, let's move on to Cosmos. Cosmos is a computing platform that combines the best aspects of microservices with asynchronous workflows and serverless functions. Its sweet spot is applications that involve resource-intensive algorithms coordinated via complex hierarchical workflows that last anywhere between minutes to hours. It supports both high throughput services that consume hundreds of thousands of CPUs at a time and latency sensitive workloads where humans are waiting for the results at the end of a computation. A Cosmos service is not a traditional microservice, but there are some similarities. A traditional microservice is an API with stateless business logic, which is auto-scaled based on the request load. The API provides strong contracts with its peers while segregating application data and binary dependencies from other systems. A Cosmos service retains the strong contracts and segregated data and dependencies of a microservice, but adds multi-step workflows and computationally intensive asynchronous serverless functions. In a typical Cosmos service, clients send requests to an API layer. A set of rules orchestrate workflow steps, and a set of serverless functions power domain-specific algorithm. Functions are packaged as Docker images and bring their own media-specific binary dependencies, for example, as a Debian package. They are scaled based on the queue size, and they may run on tens of thousands of different containers with requests taking hours or days to complete. Cosmos has two axes of separation. On the one hand, logic is divided between API, workflow, and serverless functions. And on the other hand, logic is separated between application and platform. The platform API provides media-specific abstraction to application developers while hiding the implementation and details of distributed computing. For example, a video encoding service is built of components that are scale agnostic, API, workflow, and functions. They have no special knowledge about the scale at which they run. These domain-specific, scale-agnostic components are built atop three scale-aware Cosmos subsystems, which handle the details of distributing the work. Optimus, an API layer that maps external requests to internal business models. Plato, a workflow layer for business rule modeling. And Stratum, a serverless layer for running stateless and computationally intensive functions. These subsystems all communicate with each other asynchronously via our messaging system, Timestone, which is a high-scale, low-latency priority queuing system. Each subsystem addresses a different concern of a service and can be deployed independently through a purpose-built, managed, continuous delivery process. This separation of concern makes it easier to write and test and operate Cosmos services. Cosmos supports decomposition and layering of services. The resulting modular architecture allows teams to concentrate on their area of specialty and control their API and release cycles. For example, the Video Encoder Service is the general purpose workflow facing API service that moderates incoming requests and then channels them to the appropriate leaf services, which are encoder specific, such as H.264 encodes or AV1 encodes or ProRes encodes. Such hierarchical layering of services allows us to flexibly use the services in order to serve the business needs while abstracting the complexity of the workflow from the clients. An example of this is forensic watermarking. The tool that we use internally for watermarking takes only ProRes sources as input and outputs only ProRes frames. Thus, in order to create a forensic watermarked video, one needs to create a ProRes intermediary, then call the watermarking tool, and then use its output to create the encode desired. While previously we leaked this intermediate video creation step with the higher level workflow, which was Sagan in this case, with this layered architecture from Cosmos, the client directly requests a watermarked H.264 encode, and the video encoder service creates the intermediate representation internally by calling out to the ProRes encoder service. This allows us to keep the client API stable even as the underlying watermarking tool evolves and changes. Another example is protecting clients from experimentation when we are, for example, switching out one encoder for another. With the layered architecture that you see in your screen, one can keep the client spec to the old encoder service as one explores the new encoder and only switch them to the new encoder service when we deem appropriate. In this particular case, the switch can even be abstracted away from the client if so desired. Going back to the media processing needs then, Cosmos provides several infrastructural tools to address the varied business use cases. For latency-sensitive multi-customer SIGINT, for example, Cosmos provides resource pools and warm capacity to allow for strict SLO definitions. It also allows for micro-batching, which is the trick that is found in platforms such as Apache Spark, which reduces startup latency. The idea here is to spread the startup cost across many function invocations. Similarly, for throughput-sensitive tapas, which consumes large amount of computing resources and is more concerned with the completion of tasks over a period of hours or days rather than the time it takes to complete an individual task, Cosmos provides tools such as opportunistic compute. Here, Cosmos makes use of trough or unused capacity or unused resources that are available across the company through flexible resource scheduling. Stratum, the serverless layer in Cosmos, is built atop the tightest container platform, which enables such opportunistic compute usage all across Netflix. Other features that Cosmos provides includes prioritization of tasks using Timestone's priority queuing, which enables day of broadcast and day after broadcast titles to go live on the platform in a matter of hours, as well as Nirvana, which is our observability portal. So that was a very quick whirlwind tour of the media processing at Netflix, where we covered its history and evolution, and then we quickly described our new microservice-like architecture, Cosmos, that we hope will last for the next decade of the Netflix business. Now, a quick look at some of the learnings. A project at the scale of Cosmos could bear fruit owing to our culture, which famously relies on personal judgment rather than top-down control. Software developers have both freedom and responsibility to take risks and make decisions. None of us have the title of software architect, but all of us play that role. In this context, Cosmos emerged in fits and starts from disparate attempts at local optimization. Optimus, Plato, and Stratum were conceived independently and eventually coalesced into a single vision of a single platform. The joint development of the platform, along with the application, while arduous, allowed for iterative improvements and led to user-friendly APIs and improved developer productivity. Platform developers could empathize with application developers, and application developers began to build a platform mentality so that they gave up a bit of flexibility in exchange for reliability, consistency, and scalability. Our model of microservices plus workflow plus serverless is not for everybody and works well even internally only for a majority of the use cases. Simple tasks are better architected otherwise, since the platform complexity may not be worth the benefits. Finally, we already have a significant amount of traffic flowing through Cosmos, and we hope to be 100% Cosmos by the end of next year. Thank you for what I hope was a patient listen to an informative talk. The next time you watch Stranger Things or Squid Games or The Tiger King, hopefully you will have given a bit of thought to the underlying Cosmos platform that provided that seamless experience, seamless Netflix experience that you've come to expect and love. Here's to sparking many more years of member joy. Thank you for listening.